is the AI Practitioner. So this is an AI certification, teaching you the foundational knowledge of AI club workloads. It was offerings around traditional ML pipelines. It was offerings around main G services. It was offerings around Gen AI and large language models. His course code here is the AIAIFC01. So make sure you check the course code, so you know that you're using the latest course. Consider the certification. If you want to become an AI engineer or data scientist, or you have to work with AI stuff in your developer job. If you don't know what an AI engineer is, it's someone that builds AI solutions using managing AI services, but could also be building ML pipelines or working with data scientists. To some degree you will want this certification. If you're looking to architect business use cases for ML AI Gen AI, this certification is more focused on the C-suite and decision makers to help them buy into the aid of an ecosystem for IML. But I'm gonna cram in a bunch of developer stuff because I know that people wanna do this for real and not just talk about it. If you enjoy the following tasks like stats and math, working with data, working with Python, and this is a clear path for you. If you don't, you better watch out here, cause this stuff creeps up on you unexpectedly. But for generative AI it's not so much an issue. Here is our AVA certification roadmap. And you know, again, this is just a suggestion that you can do these in any order that you want. But I strongly suggest that before you get a practitioner, do the CLAP practitioner, because a lot of the skills are expected for this. Okay. And I just need to remind you that if certifications do not validate programming, technical diagramming, code management, and many other technical skills that are required for obtaining technical roles, so do not assume that when you get a cert, you can do the job. It's part of your learning journey. Yes, of course. But you need to really make sure that you can do the skills. How long will it take to pass? Well, if you're beginner, 20 hours. If you are experienced, 5 hours. This is not a hard certification. I probably made the content harder than it had to be, but I want to prep you, for your roles in actually being able to do this stuff. You're looking about 10-hour average study time. Spend half your time with lecture and labs, other half of practice exams. Recommending you study 1 or 2 hours for possibly 14 days. Again, it won't take long to get through this course. Watch. Select your content, do the hands-on labs. Now, this certification doesn't require any hands-on experience, but I really think that you should do it, because in practice versus on paper are to completely do different things. The labs are not hard here, and it will really help cement your knowledge. In some cases I'm keeping the lecture slides light, because we're gonna be doing the lab, so even if you don't do them, watch what I do, so you get at least that experience there. Get paid prox exams, because this one has new example question types. And people said that it threw them off, right? So you can go over to the Exam Pro platform. Get your free prax exam. We also have paid ones. You can find that /AIFC01 by those paid ones. Support more of this free content. We really appreciate your support. And this stuff is hard to make. So let's talk about the domains for the exam. There are 5 domains. Each domain has its own way. This is determined how many questions that will show up in domain A. So for domain 1 we have fundamentals of AI and ML. Domain 2 we have fundamentals of JEDI. Domain 3 we have apps. Applications of foundation models. I love to saying applications is apps, and by the way, this is not a spelling mistake. I copy and paste. It's foundation models. But foundational models is also correct. Domain 4 is guidelines of responsible AI. And domain 5 is security compliance, governance AI solutions, which is not a lot to talk about, so they really overemphasize it when there's not much to say. But these 2 categories is all Jenny high, so I put a lot of Jenna in this course. Amazon Bedrock is done end to end for this. So you're in really good shape. I probably have the best course for For the AI Practitioner for the bedrock stuff. Okay, SageMaker. I do an okay job of it. SageMaker used to be SageMaker Studio Classic, and they've migrated over to this new experience, which is not very good, and so you know I'm kind of grumpy when making the content for SageMaker because I miss the old experience. And I think any of us is kind of not doing a good job reimagining that solution. But anyway, where do you take this exam, in person or online? 8 of us uses Pearson VUE for their proctored online exam system. And also for their test network. SI is gone. If you remember PSI from long time ago, 8 of us is not using them anymore. The experience with PSI hasn't been great, but I also think the reason why it was going with a single provider now is just that they can leverage that platform to its maximum and add new features like exam question test, which we'll talk about in a moment. A proctor is someone that watches the exam. So the idea is, they're there to make sure you do not cheat. So understand that is a component in the test experience. The grading here is 700 out of 1000 for passing score. I put an asteroid there because it's around 70%, because it must use a scaled scoring. You could technically fail at 70% right. So always aim for higher. There are 65 questions of the exam. 50 scored, 15 unscored. You can get 15 scored questions wrong. There's no penalty for wrong questions. Format of questions: multiple choice, multiple answer, but also ordering. Ordering matching in case I use for this exam for sure. So right now, the exam is in beta at the time that make this video, so they might change and get rid of those questions cause people don't like them. But understand that any of us is trying to exam type questions. You experiences our platform simulates them. So you'll be in good shape if you use our practice exams. Not all providers can. Even similar things like case studies, we absolutely have that in space, and we've been doing that well before this. So it was just coincidental that AWS decided to do that. 50 questions on the exam are unscored. They will not count towards your final score. Why are the unscored questions are used? To evaluate the introduction of new questions, to determine if the exam is too easy and the passing score or question difficulty needs to be increased. Discover users who are attempting to cheat. Okay. So there's lots of reasons why they do this. If you encounter questions you've never studied for, that seem really hard, keep your cool. Remember, they may be unscored questions. The duration of exam is 2.5 hours. You get about 1.5 minutes per question. There is 120 minutes with 150 minutes. C time. Time refers to the time you should allocate for the exam. This includes reviewing instructions, showing up for online proctored on, showing up for the proctor to look at your workspace, reading, accepting the NDA, complete the exam, provide feedback at the end. If it seems like I'm tired, it's cause I shot this 3 times. My microphone wasn't on, and so my voice is kind of worried out. But we'll get through this okay. The exam is valid for 36 months and 3 years before certification. I don't really know that for certain, because at the time of this exam, they didn't say that, but the general rule is that search for 8 of us is always 3 years. If you're gonna get recertified, it's gonna be you probably get it for free through a skill builder. They are always trying to do that. Let's have some real talk about certifications. I have to remind you that class certifications expect you to have foundational technical skills, like programming, scripting, SCLITI networking, Linux Windows servers, project management, developer tools, app development skills, COPS algorithm skills, and more. If you do not have these skills, and you get these cert, you cannot do the job right. This only teaches you how to do MLAI on the end of this platform, but it's missing a lot of stuff. And 8 of us likes to position this certification as a funded fundamental exam. But I find there's tons of gaps in this one. I'm producing my own foundational generic Genai certification to really fill the gaps here. But to fill the gaps, leverage Free Code Camp, their large catalog of general technical content, and We Exam Pro also make additional materials beside the certification to really help you there. That's only available in the subscription, okay? It was itself does not care about it, of a certification for hiring for their own technical roles. Certification serve as a structured way of learning with the GULPA. Now originally, certification actually mattered back in 2016-17. If you had any certification, we're talking about it. Companies took notice. But now it's more of a learning path thing. Nurse certifications can be more valuable. So the reception they have, practitioner might be more valuable. But I don't know this point, so I don't want to give you false hope and considerations. But it's good to learn this stuff and stuff like that. Understand that you might need to add 250 to 500 hours beside the certification to have the developer knowledge to perform the software or AI knowledge. If you will, so again. Just consider there's additional work to be done. If you want to work as an engineer or data scientist, we're gonna add hands-on labs to help you fill the gaps here. So if you see me taking detours, and seems like we're doing long labs, I'm trying to help you out here. You can watch them and not do them if you want. But you really should do them. Because I'm giving you real-world skills. Hearing you both keep saying that you want it. So I'm giving it to you. So some of the labs might even end up in failed implementations. Not for this certification. I think there was only one like that. That was bust, and it wasn't my fault. It was just I think we're trying to find on Amazon Bedrock, and so it just wasn't clear the span. And I just did not want to end up with a $5,000 bill or something crazy. So I did show the process and I did tell you that. But this one has next to no failures. Just the one there. But understand that it's about seeing the problems. Seeing what's worth using. Seeing what's not worth using, because these certifications are marketing tools to convince you to utilize them, but I'm here as your community hero. Actually, I'm an AWS community hero to tell you the real truth about these services, and which ones you should use and maybe avoid. And I want to be really clear with that. We do try our best to clean up infrastructure, but you should always be proactive and check if the resources are running. You're responsible for the cost. And spend your AWS account. In the 8 of Us Practitioner course, I show you budgeting. So I'm not showing in this course by doing this one. And by the way, in this course I actually had unexpected spend. I usually don't have it, but I had it with a SageMaker canvas. It was almost $400-500 Canadian. Cause it's US dollars converted afterwards. And it's just one of those services where they really misled you. Not intentionally, but because of you. I was so bad, and I really pointed out, and I even tell you, don't you say make a canvas and just watch me do it. So be very careful with spend. But I do my best, but you are responsible. Just remember that, okay? And we're looking at the 8 of Us certified practitioner. I do want to point out that right now, the exam is in beta. So generally, I would recommend for you to wait to go out of beta, because beta means that the exam questions are gonna change, and often betas for testing to see whether the exam is good or not. Not really for getting that validation. But anyway, if you want to go sit early you can, but again, my recommendation is to wait. The exam guide is very unlikely to change, so it doesn't usually change too much from the beta experience. It's more about the exams. So this is gonna be fine. But let's scroll on down and take a look here and see what they're recommending. So familiar with AWS core services. Share responsibility model. I am global infrastructure. This is all the stuff that gets covered in the AWS Cloud Practitioner. So you should have your Cloud Practitioner before proceeding for this certification. Things you don't have to do: develop coding, ML algorithms, implementing data engineering feature techniques, hyperparameters, bullet deploying AI pipelines, conducting math or statistics, basically nothing. You don't have to do any hands-on, but I gotta tell you, I pack in hands-on stuff. Because I think that if you do some hands-on that, it's going to really help cement that information. Your head, there's no reason not to do it. Because you know we can read something on a paper, but it has nothing to do with what's actually happening. So you should do hands-on labs. And I have hands-on labs for you. I have a lot around Amazon Bedrock, just because I feel that that was should have been more strengthened in this certification, and so, or just knowledge in general, because such a large product. But I spent a lot of time in Bedrock. Let's roll down here and take a look. So we have multiple choice, multiple response ordering, matching case studies. These three are new, not new if you're from Azure, because that seems like a similar thing from over there. But yeah, these are new question types. We have 15 unscored questions. So continue on to here. The results is between 100 and 1000. With a minimum passing score of 700. Okay. Your score report can contain tables of classifications of performance, which I'm not really interested in. We'll scroll on down. Let's take a look at the domains. We have fundamentals of AI ML, fundamentals of JEDI, applications of foundational models, guiding of responsibly AI, and then security. So we'll take a look here, and they rattle off a bunch of different terms. And so I do my best to cover as much as I can here. The problem is that it's not very extinct, or exactly what it is they want you to know. And because right now betas, I don't know exactly what's gonna show up on there, but I did a lot of coverage here to have as much as I can. Over here we have recognized app AI workloads. They are just talking about like when you should use them, when you should not use them. Do you know all the managed services? And we cover all those managed services here. Then we're talking about SageMaker and the analog pipeline, all the steps and all the core SageMaker features and services you should know. Then there's about model performances. I give this a bit of extra time in the course, is because you know, they become valuable later down the road, but they are not super technical. So you're not gonna have a hard time with that. For GenAI we have a lot of stuff, and I really dot the I's on GenAI. Not because, well, it's not like I'm huge about GenAI, but I just happen to be building a lot of GenAI projects, so I just was able to pack in a lot of good stuff here. I think a lot of companies, again, this is where their focus is gonna be when they're taking the AI practitioner. So a lot of information on that, then you know. They're talking about more of the other services, like Party Rock, Bedrock Playground, Amazon Q. By the way, Amazon Q is terrible product. AWS keeps telling me like, oh, it's new and improved every like 2 weeks, and I come back and doing this is garbage. I don't know why they keep promoting it, but I guess they've invested a lot of energy into that product, and unfortunately, it's just not very good. So sorry, I don't have anything nice to say, but maybe the future is better. But every time I look at it, it's bad applications of foundation models. So yeah, we're talking about not just foundation models, but just types of, where they call this application foundation models, but yeah, just general's generative AI knowledge. It's weird that they just have this here, cause it's basically that section as well. And then responsible AI, you know. There isn't a whole lot to say about responsible AI. It's kind of weird that it has so much attention here. But we literally just spend one video on it. And there's 3 other videos of services to look at, but you pretty much guess, Like what is responsible and what's not. So it's not like that hard. We'll go down below here. Not a lot to talk about security. I mean, they listed a bunch of stuff in here, but some lot of things that they were listing don't even exist yet, so And not, I don't mean cause it's a beta. I just mean like they're talking about things that just don't exist. Like they haven't been implemented. So I think that this is just AWS is not doing a very good job putting together these exam guides as they used to. They are really throwing a lot of stuff at the wall here, but that's okay. I'm gonna make sure you come through this pretty well here with no problems. There's appendix of a lot of services, and what is in scope and what's out of scope, so here you can see a bunch of services here. And not all of them are in the course. But I listed the ones that I thought were most relevant, and what my experience was, and what logically made sense. And yeah, so there you go. We are taking a look at the definition of what is artificial intelligence, and we really want to put this against the terms of machine learning, deep learning and generative AI so that it's very clear what the differences are. Often, people just say AI when they mean ML or deep learning, so understand that these terms are not used correctly often. But people generally will understand what you're trying to say, so it's not a big deal if you use them out of turn. But let's make sure that we know what they are. Let's first take a look here at artificial intelligence, also known as AI. These are machines that perform jobs that mimic human behavior. Okay. That's the key thing here, is that they are human-like, or doing tasks that you'd expect a human to do. And that is clearly a very broad term of what is AI. And so you can see why a lot of things are attributed to being AI. Then you have machine learning. And machine learning, initialized as ML, is machines that get better at a task without explicit programming. Now, of course, we have to code a machine learning model. But once we have that model and we pass things into it, it's able to complete its task with its very complex algorithms. So you could also just think of it as it's a special algorithm to perform a task that would negate you having to do calculations or programming or things like that. Then we have what is deep learning. And when we think of a lot of the AI stuff, we're usually thinking of deep learning because it's these machines that have an artificial neural network inspired by the human brain to solve complex problems. So you probably have this. You've probably seen a graphic of it, like these nodes, and they're interconnected and they go through layers. That's deep learning. A lot of people call that machine learning, right? But no, that's DL. Then we have Gen AI. So Gen AI, which is more of a marketing term. But generative AI is a specialized subset of AI that generates out content such as images, video, text, and audio. Now I don't have it in the graphic on the left, because it's hard to say where does it go. Does it go here? Right, because it is a subset of AI. But technically Gen AI often utilizes deep learning. Cause when we think of it, and my line's not drawing here today, but when we think of it, there we go, there's the line. Is that a lot of DNA techniques, like large language models or vision models, things like that, are utilizing neural networks. So it is deep learning, okay. Alright, so I know we keep talking about what is AI. What is Gen AI, but we're gonna cover it again, just so that it becomes more clear. From different perspectives. So let's talk about what is artificial intelligence. So AI is computer systems that perform tasks, typically requiring human intelligence. So these include things like problem solving, decision-making, understanding natural language, recognizing speech and images, and an AI's goal is to interpret, analyze and respond to human actions. It's there to simulate human intelligence in machines. We use the word simulate, we're talking about mimics aspects, resembles behaviors. But what we're not talking about is emulation, which is replicating exact processes and mechanisms, as if you created literally a virtual human brain. That's what emulation would be. So AI applications are vast, include areas such as expert systems, natural language processing, also known as NLP, speech recognition, robotics, and more. AI is using various industries for tasks such as, we're talking about business to consumer. So think of a customer service chatbot. If we're looking at e-commerce, think of a recommendation system. If we're talking about the auto industry, or maybe we're looking at automated vehicles. If it's medical, then medical diagnosis. There's a lot of applications for AI. But it's a broad application for all sorts of things. Now let's take a look at generative AI. So generative AI are often initialized as Gen AI or said as Gen AI, is a subset of AI that focuses on creating new content or data that is novel and realistic. It can interpret or analyze data, but also generate new data itself. It often So like types of content producers would be text, images, music, speech, and other forms of media. It often involves advanced machinery techniques. So it could be using things like GANs. It could be using VAE, so variational autoencoders. A lot of current LMS use the transformer architecture. So if you're using Tattoo-BT or Claude Sonnet or any of the popular ones, they are basically all transformer architectures. General AI has multiple modalities. And when we say modalities, is like, think about your senses. You have touch, taste, hearing, smell. So modalities are the kinds of content or senses that a model has. So we have vision. So real sick images and videos, text, jarring human-like text, audio, composing music. Molecular, which is more of an interesting one. So drug discovery via genomic data. And I want to make it clear again. We're talking about large language models, but LMS large language models. I will generate out human-like text, and is a subset of Gen AI, just one modality of the many modalities. But it's often conflated as being AI or Gen AI just because it's the most popular and in demand right now and the most developed. So just make sure that you understand that Gen AI and AI is not all about large language models. It's just one modality, one application of the broad sense of AI and Gen AI. Now, let's just make sure we have a side-by-side comparison. And then I'm sure after this, you'll definitely know definitively the difference between AI and Gen AI. So in terms of functionality, AI focuses on understanding and decision making, whereas Gen AI is about creating new and original outputs. For data handling, AI analyzes and makes decisions based on existing data. Gen AI uses existing data to generate new and unseen outputs. In terms of applications, AI spans across various sectors, including data analysis, automation and NLP, and healthcare, where Gen AI, yes. I see the spelling mistake. It's creative and innovative, focusing on content creation, synthetic data generation, deepfakes and design. So there you go. Let's talk about Jupyter. So, Jupyter Notebook is a web-based application for authoring documents that combine live code, narrative text equations and visualizations. And before it was called Jupyter Notebook, it was known as IPython's Notebook. And Jupyter Notebooks were overhauled and then turned into an ID called Jupyter Lab, which we'll talk about here in a moment. But you generally want to open notebooks in labs. And the legacy web-based interface is known as Jupyter Classic Notebook, and to be honest, I get confused between Jupyter Lab and Classic. I think most things that use these days are Jupyter Lab. But the confusion is because we just call them notebooks, even though Jupyter Classic Notebook is, nope, that the older one and the nearer one is Jupyter Labs. Let's go take a look at Jupyter Labs. Jupyter Lab is the next generation web-based user interface. Has all the similar features as the classic Jupyter Notebook, in a flexible and more powerful user interface. So it has notebooks, terminals, text editor, file browser, rich outputs, and the way I think that that you're using a Jupyter Lab is that it will have these tabs here on the side, and a bunch of functionality. So Jupyter Lab will eventually replace the classic Jupyter Notebook, and that's kind of true because but not fully, because in some places I do come across classic notebooks launching them up but for the most part, functionally it has been replaced. Then we have Jupyter Hub. So Jupyter Hub is a server to run Jupyter Labs for multiple users, as intended for a class of students, a corporate data science group, scientific research groups, and so it has some components underneath. You will come across notebook-like experiences that are like Jupyter Labs. So some companies will extend the functionality of it. One example is StageMaker, our studio classic. For whatever reason, 8 of us spent all this time creating extensions and extending Jupyter Lab, and then they decided, no, we're not gonna have extensions anymore, and we're just gonna use the vanilla version. But there's also things like VS Code that has notebooks, or Code Lab that have notebooks. And this code is like its own kind of notebook thing. It's not Jupyter Labs, but it's Jupyter Lab compatible. So just understand that you'll come across things that are notebooks that look like Jupyter Lab, but they are not necessarily Jupyter Lab. Okay. Let's take a look at natural language processing, also known as NLP and in machine learning. It's a technique that can understand the context of a corpus. A corpus is a body of related text, the text that you are working with. And NLP intersects with computer science and linguistics. So if you know a lot about the nature of spoken and written language, then computer science here is going to meet in the middle here so that we can make sense of it using algorithms. So NLP enables us to do things like analyze, interpret text within documents, emails and messages, interpret or contextualized spoken text, like sentiments analysis, synthesized speech, such as using a voice assistant talking to you, automatically translate spoken or written phrases and sentences between languages in a, interpret spoken or written commands, and determine appropriate actions. Another thing you'll hear a lot is language understanding, which is supposed to be, it's more like a specialized subset of NLP. That just goes farther to understand more traditional older ways of doing NLP. But anyway, what I'll do is we'll just take a look at this very simple flowchart to give you some idea of things that are related with an NLP. This is mostly just get you exposed to some terms. It's not important to remember what these are, and I can't even describe them off the top of my head. But again, just get you exposure to NLP terms so that when you see them later, you'll go look above and be like, I remember seeing that term here. So here we have like text wrangling, pre-processing language understanding, so structure and syntax processing functionality, which is what the NLP does for you in the end, but text right in the pre-processing is where you are preparing a text to be put into possibly a machine learning model, or maybe you're using it for some kind of analysis or something like that. And so this is basically taking text and formatting it, changing it. And so what could we be doing here? Well, we could be doing conversions. Maybe we're lowercasing things and we were uppercasing things. Maybe we're turning contractions into their full forms. Or vice versa, sanitation. This is where you are maybe stripping out a smell or special characters. Or you are removing stop words when you have stop words later on in your ML models. Tokenization, which is converting the text into a vector embeddings. We have stemming, okay, we have lemmonization. So there's a lot of things here. But you can see it's mostly just like formatting the text to be utilized for something else. We have language understanding. So these are processes to make sense of the text. So part of speech tagging. So is this an adjective? It's a noun, things like that, trunking. How can we break up the text and then work with those chunks later on down the road? So that still makes sense, dependency parking. So you know which word relies on other words. And what relationships do they have to their once constituents, a person. Very hard for me to say, but like imagine a trap green, a trap green. And so like a noun has an adjective under it, which has another thing under it. If you look it up and go to Google Images, you'll know what I'm talking about. Then we have process functionality. What are we using MLP for? So we have name entity recognition. This is where you have a body of text and it's highlighting important words, like maybe important nouns it thinks you care about, or things like that, or personally identifiable information. We got engram sentiment analysis. Is this text positive, negative, happy, sad? Information extraction. What are we trying to get out of a large body of text? Same thing with information retrieval. Questioning, answering, topic modeling. So again, not super important to know reason depth right now. But the things that are important, we will see these terms again and you'll know what they are then. So don't worry about trying to memorize this now, but just get that exposure to NLP terms, okay? Hey, this is Andrew Brown, and we're looking at the concept of a regression. And this is a process of finding a function to correlate a label data set into a continuous variable, or number also. Imagine we need to predict a variable in the future, such as the weather was it gonna be next week. And so the idea is that you're going to plot your data onto a graph or vector space. Our dots are represented as vectors, and we're gonna draw a line through it, which we call a regression line. And the point of the regression line is that is our prediction, so if this is going over time. Basically temperature, that is how we are figuring it out in the future. What things are going to be. So the distance of a vector from the regression line. And just get out a different colored pen too. Other than red. So maybe cyan, so imagine this dot here to the line. That's what we're gonna call an error, because the idea is that things that are closer to the line is the prediction, and things that are farther away from the line are an error from the line. So hopefully that makes sense. There are different progression algorithms used, that we use to predict future variables. So we have mean squared error, a root mean squared error, mean absolute error, and so based on the algorithm that you use to draw your line. That's gonna change on the prediction, okay? Let's take a look at classification. This is the process of finding a function to divide a label data set into classes or categories. So the idea here is we're going to predict a category to apply to the input of data. So will it rain next Saturday? Is it gonna be sunny or is it gonna be rainy? So the idea is we have our data. We're plotting it on a graph, but we're drawing a classification line that divides the data set, okay? And the idea is that if it falls on one side, then it's sunny. It falls on the other side, then it's rainy. And so again, if you have a different type of algorithm, that's the thing that's doing the division, it's going to have different results. You have a logistic regression, a decision tree, random forest. You can use a neural network. You can use a Navy base. I always say that wrong, so I do apologize. Or you can use KNN. Or you can use a support vector machine at SVM. So just understand that there could be more algorithms. But these are the common ones, and if you want to learn more about how these different algorithms will change, just look up on the internet what that would look like, and there's definitely visualizations out there, okay? Let's talk about clustering. This is the process of grouping unlabeled data based on similarities and differences. The key word here is unlabeled. When we looked at our classification, that was labeled data. So the idea here is that we're grouping based on similar user differences. So imagine that this grouping of dots that are close together, we determine that that is Windows. And this group of dots are Mac computers. And just like classification progression, you have different algorithms are gonna give you different results. And the reason why I show you these algorithm names is because when you have to do classification, regression or clustering, you're going to see these names because you have to choose what algorithm you want to utilize. Right now it's not so important to know them. But when they are important, we will look at them in more detail, okay? So we are going to dive into the types of machine learning in other slides and more detail, but this is just kind of an overview, so that you can kind of see these terms up front. So just quickly go through this here, and we're gonna group them based on what they're trying to do. So the first is learning problems. We have supervised, unsupervised, reinforcement. These are three terms you're gonna hear quite a bit with machine learning. The key thing here is that supervised is where you have labeled data and unsupervised is where you're working with unlabeled data. For reinforcement, this is an agent that operates in an environment and must learn to operate using feedback. And this kind of sounds like agentic workflows or agentic coding. We're talking about Gen AI, which we'll learn about later. But the idea is like, imagine you wanted to make a machinery model that played the Mario or the Sonic video game. That would be using reinforcement learning. Okay. So we have hybrid learning problems. So we have semi-supervised, self-supervised, multi-instance. So semi-supervised is where you have a mix of labeled and unlabeled data. You have a lot of unlabeled data and a little bit of labeled data, and so that's kind of a mix between supervised and unsupervised. You have self-supervised and I believe that this is where the idea is that it can label its own data. I think, but we'll find out later on in future slides. We have multi-instance where we have examples of unlabeled data. And so then we just kind of bag them together. Again, we'll cover that later on. We have physical inference. So here we have inductive, deductive, and transductive. So using evidence to determine the outcome you are. Then we have deductive, using general rules to determine the specific outcomes. And then we have transductive, used to predict specific examples given specific things from a specific domain. Okay, then for learning techniques we have multitask, active online transfer, and ensemble. So multitask is fitting a model on one data set that addresses multiple related problems. Active is the model is able to create human operate during the learning process. Online is using available data and updating the model before prediction is made. Kind of sounds like RAG. We're talking about Gen AI. But again, this is just general machine learning, right? So we have transfer model is first trained on one task. And then summer, all the models used as a starting party for related task, and then we have ensemble, where two or more models are fit on the same data. And the predictions from each model are combined. So yeah, we're gonna see these terms again. But just trying to get it up front here for you, okay? Let's take a look at the divisions of machine learning. This is just another way to break up machine learning. And these terms you're gonna see are more, and how we're gonna structure our upcoming slides here. So I just wanna give you a quick overview here. So we have classical machine learning. An advantage of classical machine learning is the data. Simple, you have clear features. And generally classic machine learning is extremely class efficient compared to other types of machine learning. But this is where you have supervised, unsupervised kind of stuff. So when you think of classical machinery, think of those two things, supervised and unsupervised. Learning. Then you have reinforcement learning. This is when there is no data. And the idea is that the model is going to, through trial and error, figure out what is the right thing to do. This is where we have real-time decision-making game AI. So we talk about Mario or Sonic like the ML model. Playing those games and failing again. And again until they can pass the game learning task. Or robot navigation. So think of autonomous driving vehicles. That would be a good case for reinforcement learning. We have ensemble methods. When quality of data is a problem. So then you are going to have different strategies to work with, multiple models or algorithms to have a better outcome. And here we have things like bagging, boosting, stacking. Okay, and so you'll see those terms like boosting. You'll definitely see the word boost more when we get to that we have neural networks and deep learning. You should just really think of deep learning neural networks. This is when the data is complicated and all the features are unclear. This is where you use neural networks, like a convolutional neural network, a recurrent neural network, a Ganso generative adverse spiral adversarial network. Multi-layer perceptrons. MLP autoencoders. I just have a really hard time pronouncing these things. But yeah, you're gonna see these terms again, so don't worry about it right now. Let's take a look here at classical machine learning. And so when we say classical, we're talking about algorithms that have existed for quite a while, maybe as early as the 1950s. Because we had these mathematicians. And they figured these out. And a lot of these things actually relate to statistics. Right, so we're taking statistics and utilizing them in these algorithms in our computing spaces, so hopefully that makes sense. But yeah, it's the cold classical ML, because we are dealing with older algorithms. And one example would be nearest neighbor algorithm, which was invented in 1967. And lots of companies today definitely could utilize classical machine learning to solve business problems. Just because they are old does not mean that they are not good. It's just a matter of organizations knowing how to adopt classical machine learning. So let's talk about first supervisor learning. So this is where we have data that has been labeled into categories. And this is great when we are doing something that is task-driven. We are trying to make a prediction because the idea is we have this labeled data. And so then we can bring unlabeled data and tell the machine to label it right. So here we have classification. So imagine we want an outcome. This would be to predict the cat, what category something belongs to. I use case here to be identity fraud detection. We have regression. This is where maybe we want to predict a variable in the future. So we're trying to figure out a market forecast. And we cover classical regression, so you should know what these are. If not, You will know about what they are soon enough. Cores will cover them more than once. Then for unsupervisory. We have data that has not been labeled. Okay, this is where things are data-driven. So we recognize a structure or a pattern. We're not making a very specific prediction. Here we have clustering. So the outcome of something. So you group data based on similarities or differences. Example here will be targeted marketing association. So find a relationship between variables through association. This case here would be a customer recommendation. We have dimensionality reduction. So here, help reduce the amount of data or pre-processing. This is a problem, you have a lot of data. And this use case here would be big data visualization. So yeah, there you go. Alright, let's compare supervised versus unsupervised learning. And I know we've already talked about it, like twice before, but we're gonna talk about again and then again. Because I'm just trying to give it to you in different perspectives, so that you really know the difference between these. So let's talk about what is supervised learning. So this is a machine learning task, a function that needs to be provided training data. And the training date is when you provide label data, the correct answers, and the machine can learn from those results. So show me how to do it and then I can do it on my own. That's what's happening here. And so for supervisory models, we have classification regression. What about unsupervised learning? This is a machine learning task, or function that needs no existing training data. For this, it will take the unlabeled data and discover its patterns, applying its own labels, so I'm an independent worker. I can figure this out on my own right. And for this, these unsupervised learning models, we really should have put the UN on that there. Let me just fix that there. Unsupervised, we have clustering association. Dimensionality reduction. And so supervising tends to be more accurate than unsupervising, but requires more upfront work. Whereas, unsupervising still requires human intervention to validate the results. So hopefully that is clear. Okay, let's review it one more time. I know it's getting tiresome, but it's very important that you remember the difference between unsupervised and reinforcement. So, supervised learning is where the data has been labeled for training. It's task-driven and you're making prediction. This is when the labels are known, and you want a precise outcome, when you need a specific value return. And so here we use classification regression as examples of supervised learning. There's more than just those two, but that's what I want to know for now. We have unsupervised learning. Data has not been labeled. The ML model needs to do its own. Labeling is data-driven. You're recognizing a structure or pattern. When the labels are not known, the outcome does not need to be precise. When you're trying to make sense of data, here we have clustering, dimensionality reduction association. Then you have reinforcement learning. So there's no data and there's an environment. And an NL model generates data, and many attempts to reach the goal. And this is decision-driven. You have game AI learning task robot navigation. So hopefully that is clear and it's in your head. We're gonna repeat these again. But it's gonna be less of this. And more detail, okay? Let's talk about supervising models. And we're gonna cover classification and regression. Again, just so that we really know that we know what these things are. So classification is a process of finding a function to divide a dataset into classes or categories. So imagine, will it be cold or will it be hot tomorrow? Right, so very clear it's either one or the other. It's gonna fall on one side of the line or the other one. We have different algorithms we can use like logistics progression, k-nearest neighbor support vector machines kernel SVMS, Navies-based decision tree classification, random forest classifications, and we're listing a lot more. Here we have what is regression. Regression is a process of finding a function to correlate a dataset into a continuous variable number. So what is the temperature going to be tomorrow? And here we have things like simple linear regression, multiple linear regression, polynomial regression support vector regression, decision tree regressions, random forest regression. Just again want to continuously repeat that, so you know what these things are, okay? Let's take a look at unsupervised learning. So what can we do here? We have clustering again. We've covered these prior, but I just really want to make sure that you know what they are. So clustering is a process of grouping unlabeled data based on some similarities and differences. Right, so we use an example previously. Is this a Mac or is it Windows? Here it's about age and something else. And so it's saying do these people have cholesterol? Are they high risk or low risk? For clustering algorithms, we have k-means db scan k-modes. Then we have association. So association is the process of finding relationship between variables through association. So the idea is that if somebody buys breads, then suggest butter, because based on previous combinations, we know what people want. So there are different algorithms for that. I cannot say those words, so I'm not even gonna attempt it. You can see them here on the right hand side. We have dimensionality reduction. This is where we're reducing the amount of data, or retain the data integrity, often used as a pre-processing stage. And we have lots of algorithms for this. Principal component analysis, linear discriminant analysis, generalized discriminant analysis, singular value decomposition, a laden, a director. I can't say that word. There's just too many words that are too hard to say, but there's a lot for dimension. Dimensionality reduction, yeah. So hopefully you can remember those things. Classification regression, clustering association, dimensionality reduction, okay. Let's take a look here at neural networks and deep learning. First, defining what are neural networks. So these are often described as mimicking the brain. You have a neuron or node that represents the algorithm. The data is inputted into the neuron, and based on the output, the data will be passed to one of the many connected neurals. The connections between neurons is weighted. The network is organized into layers. There will be an input layer, multiple hidden layers, and an output layer. You could technically have one hidden layer, but often you have multiple layers. If you have 3 or more. Now we're talking about deep learning. If you have less than 3, that's just a neural network. And just look at the visual for a moment. Cause each node or neural, remember that it has its own algorithm, like how it's going to process that data. And I'm pretty certain that most neural networks are the algorithm is gonna be same for all the nodes. But we'll talk about that as we dig deeper into the neurons themselves. But then there's a concept of a feed for neural network, which is initializes FNN. I don't know why it's not FFNN, but whatever. So these are neural networks where connections between nodes do not form a cycle. That means that they always move forward. So data moves forward, okay. We don't have neural networks going back and this way and that way. They are just going one direction, which is forward. Then you have back propagation. This is where after things ran into like everything's ran through, it's gonna move backwards through the neural network and adjust the weights. Okay, to improve the outcome on the next iteration. So after it's ran it actually to update all the weights, and that is back propagation. This is how a neural network learns. It has to do back propagation. Okay, then we have a loss function. So it's a function that compares the ground truth to the prediction determine the error rate. So how bad the network perform ground truth right is data that is labeled that you know to be correct. Okay. Now we're talking about how these neurons are going to have their own algorithm, right? Cause up here we say that it represents algorithm. So this is where we have these algorithms, which you call activation functions. So an activation function is an algorithm applied to a hidden layer node. It's one of these things right here. Let me just get my pen out again. One of these that affects the connected output. And so example that would be RELU or RILU. I don't know how to pronounce it properly, but I recognize it But we will be looking at activation functions when we look at and draws a bit soon here. There's the concept of dense. So when the network layer increases the amount of nodes, we call it more dense. And when the layers decrease the amount of nodes, we call it sparse, okay. So when we see increase, it's dense. If it's decreasing, it's sparse. And for deep learning algorithms, we have supervised and unsupervised, just like with classical machine learning. And so on the supervised side, we're gonna see things like RFNN, RNN, CNN. So you are passing in label data for this to work. For unsupervised learning, we have DBN's essays, RBMSS, and not important to really remember this. But I just wanted you to know that they have supervised unsupervised learning. For deep learning, okay. Let's take a look at what a perceptron is. So a perceptron is an algorithm for supervised learning of binary classifiers, invented in 1943. And then the machine was built in 1957. So the Mark I perceptron, which is the name of the machine, it was able to do some form of image recognition. What that would be, I don't know. I was able to extrapolate that. But you can see all of the interconnected work. Just kind of like the human brain would have, where you have these connections and layers. And so this is kind of where the idea of a neural network, came from, and the fact that it's so old, just shows you that, we've been doing ML longer than you think. But yeah, hopefully that lays the ground of the word perception. But we'll take a look now at a perception network. Let's take a look at a basic perceptron network. And you might be saying, why are we so interested in this very old type of network? It's not old, this is neural networks, they are perceptron networks. So, just goes to show you that the concept is not new. Just that we have now scaled it. And we have a lot more compute, and we're not connecting everything by hand, right? So a basic perception has an input and output layer. Each layer contains a number of nodes. Nodes between layers have established connections that are weighted. So here is that example. The amount of nodes in the input layer, right, make my hand out here, over here, is determined by the number of dimensions of the input. A vector, what does that mean? The number of dimensions of an input of vector. So vector, remember our graph. We're taking a dot and putting it somewhere. So if you had a graph or a vector space that had an x and a y, then you have two inputs for the node, right? You have x and y, and it doesn't have to be x and y. Could be different kinds of values. But that's the point there, okay? So the input layer is just connection points, okay? This input layer, nothing that this layer does will modify the data, okay? Just the starting point for it. So the amount of nodes in the output layers, determined by the application of the neural network. So if you have a yes and no classification, then you would only have one output no. Because you just want to know, is it yes or is it no? Is it 0 or is it 1? So it would not matter if there was 1,000 input nodes. But if your classification is yes or no, you only need a single node for that, right? The output nodes and other layers can modify and compute new values based on the input of data. Okay, and so data moving between nodes are multiplied by the weights, right? So that is what a weight does. It affects the strength or the weakness of the number of what you want to adjust it for. The weights will be modified during the training process to produce a better outcome. So hopefully that is clear, but the only thing that you don't see here is those hidden layers, those additional layers. But anyway, we'll move on to now talking about how the algorithm of the actual neural or the neuron works, okay? Let's take a look at activation function. So when data arrives to know that can perform a computation, all arriving input of data is summed. And then activation function is triggered. So the idea here is you have let's say you have two nodes and you have connections to the YEP. The output node, notice that it's summing That is the mathematical symbol for our sum. And then we have a math like a battle cool symbol for a function, right? It's going to sum it, and then trigger the activation function. So, the activation function acts as a gate between nodes, and determines whether output will proceed to the next layer. The activation function will determine if a node is active or inactive based on its own output, which could be a range between 0 to 1 to -1 to 0. And there's all sorts of activation functions you can put in here and this is not the full list. And depending on if you're watching a beginner like course, I gonna have this video in more than one course, so if you're in a beginner course, we will not show you the types of activation functions, like literally how they work, but in a more advanced and not long we will, because you will want to know them there. So just understand that you know, if you don't see exactly what these look like, it doesn't matter right now, okay? So we have linear activation function, so it can't do back propagation. That's what linear activation functions can't do. So here just passes along the data that we have. Non-linear activation function, so can do back propagation, can stack and have many layers. Here we have binary steps, so if greater than threshold then activate. We have sigmoid using binary classification, susceptible to the vanishing gradient problem. These are things again. If you are doing real ML with me here, then we will talk about them. If you don't see it in the course, it's because I'm trying to make things easy on you, okay? We have 10H or 10H, I'm not sure how to pronounce it. This is a modified scaled version of sigmoid, still susceptible to the vanishing great gradient problem, which is something we really want to avoid. Reloop again, I don't know how to say it properly. Mostly we're missing an L there. Nobody tell me that, okay? Mostly commonly used activation function, and will treat any negative value as a 0. We have leaky ReLU, this counters the dying ReLU problem, with a small slope of negative values. Primatized ReLU, so type of leaky ReLU, where the negative slope is fixed at 0.01. X exponential. Linger unit similar to reload. No dying ReLU problem saturates negative large numbers. We have switched, this is an alternative to the reloop by the Google Brain team. Max out, use it in a max out layer. Choose the output to be the max of inputs. Softmax, this is something you'll see a lot of. You're looking at architectural diagrams. Like if you look at the transform architecture, look for the word softmax. You'll always see these near the outputs. Converts the outputs of probabilities for the multiple classifications. So yeah, you know, I might cover these, or we might not based on that course. But anyway, that is the activation functions, okay? Alright, so we're taking a look at activation functions. The first being the linear activation function. It is also known as the identity function. It's a straight line, as you can tell here. The model's not really learning. It does not improve upon the error term. It cannot perform back propagation. It cannot stack layers, only ever has one layer. This means your model will behave if it's linear, so no longer handle complex nonlinear data. Other range is that it's unbound, so it's infinite, it's derivative 1. What you put in is what you get out. So you know, why would you want to use this? I think that it's used for inputs because you know, if you're just passing something along, then that's totally fine there. But if you had multiple hidden layers of this, it's not gonna be very useful, but there you go. Let's take a look at binary step activation function. So this function will either return 0, 1 if the value is 0 or less it will return 0. The value is greater than 0, it'll be 1. And that's why it's called a binary step function. 'Cause it's clearly in one place or the other. It could only handle binary classification, so on or off or true or false. It has a range of 0 or 1, it is bound. So it's not infinite. It's one of the earliest used activation functions. Not used much today, but you know. When we were looking at that example of like producing yes or no, you could see that this would be the activation function on the output function, right? Because that'd be very clear. But you can see this is very simplistic, okay? Let's take a look at the sigmoid activation function, which is a logistic curve that resembles an S shape. So there it is. It can handle binary multi-classification. So think cow or pig. As we are looking at multiple types of classification. We can now stack layers. We have ranges between 0, 1. It tends to bring the activations to either side of the curve, with clear distinctions on prediction. One of the most widely used functions. Near the end of the function, y responds less to x. So this causes the vanishing gradient. What we're talking about, we say vanishing gradient. Like look at this, it just goes and it vanishes into the gradient. That's what it's talking about. The network refuses to learn further, or is distractedly slow, so if values are over here, then you're gonna run into some trouble. So sigmoid is analog, meaning almost all neurons will fire. The activation will be both dense and slow. Slowly and costly, so think about that. Binary step, because if it's binary step is either on or off. Cause remember that the purpose of it is that if it's 0, it's not gonna pass data along, if it's 1 it is. So because this it I mean. It could technically 0. But like even if it's here, it's a little bit on, right? It's always on. Or it's just like really on, or it's teeny tiny on, right? So there you go. Alright, I want to admit something is really embarrassing. But when we initially listed out those activation functions, I think I swapped the H and N. So I called it turn H when it's just ton. And that's why I was saying ton before, because in my mind I knew it was Tom, but like the H was off, so I said tan A. So I do apologize for that, but it is torn and is the same as a sigmoid function, but it's scaled and it's made larger. So looks really similar. So it can handle binary multiclassification, because it's analog just like the other one. We can stack layers. We have ranges between -1 and 1. The gradient is stronger, so it has a steeper curve. It still has a vanished ingredient problem, like the sigmoid but versus ton and sigmoid is based on use case, so ton can assist in to avoid bias ingredients. Ton can outperform sigmoid, so you know it depends if you need to do it or not. Right. Let's take a look here at real use. A realist answer. Rectified linear unit activation function, where the positive axis is linear, and the negative axis is always 0. So looks like that, and again. Just remember, the point of activation functions is that it's either on or off or always on to some degree or not. So here the range is 0 to infinite. So we have a positive axis that is unbound. So with sigmite and tan atoms, it fires almost all the neurons, and this leads to things being dance. Remember we said dance as in There's it's adding more information as it goes, as opposed to being the same or less. It's slow, it's costly. So the real is will sparsely trigger activation functions because of its negative axis gradient being 0. So you have you know something is really low. It's going to be 0, it's not going to be a teeny tiny bit on, it's less costly. But it's more efficient, so it's a lot faster. The negative axis, with a 0 grading, has a side effect called the ReLU dying gradient, so the gradient will go towards 0 and will be stuck in 0, because variations, adjusting due to input or error, will have nothing to adjust to, so the nodes essentially die. Okay. Let's take a look at leaky ReLU activation function. So leaky, rectified linear unit activation function, is where the positive axis is linear, and the negative axis has a gentle grading closer to 0. Do you notice that every time we look at one of these, it's trying to solve a problem and try to be better? So hopefully, you're seeing that as we go through these activation functions. So it's similar to the ReLU, but it reduces the effects of the ReLU dying gradient. It's leaky because the negative axis leaks, which causes some nodes not to die. We have also primatized ReLU, which is leaky ReLU, where the negative slope is 0 point, or 0 to 0,1. We have ReLU 6, where we have ReLU, where the positive axis has an upper limit, so it's not infinite. So the idea here, it's bound to a max value. Okay. Let's take a look here at exponential linear unit, also known as ELU. It has a slope towards a -1 axis. It has a linear grading in the positive axis, So that's what it looks like. Kind of like what was the last one? I already forgot it was called, but you know, the one where it was 0 in the one direction there. But anyway, so something between ReLU and unleaky ReLU So ELU slopes towards the -1. Negative value. It pushes the mean of the activation closer to 0, meaning activation closer to 0 causes faster learning, and convergence ELU avoids the dying ELU problem. It saturates for larger negative numbers. So everything is a trade-off with these things, okay? Let's take a look at the swish activation function. So it has a slope that dips and eases out to 0. In the negative axis, it has a linear gradient in the positive axis. So kind of looks similar, but like a little bit different. Swish was proposed by the Google Brain team as a replacement for ReLU. It's called swish because of its swishing dip. It looks so much real, but it's a smooth function. It never abruptly changes direction. It is non-monotonic, so does not remain stable. Similar to ReLU, will have sparsity very negative. Very negative eyes will zero out. There are other variants in the swish families. We have mish hard swish and hard mish. Let's take a look at max out. So this is a function that will take multiple inputs, and it will select the maximum value and return the value. So the max out is a generalization of ReLU and the leaky ReLU functions. Max out neuron would have all the benefits of ReLU neurons without having the dying ReLU. Max out is that it's expensive as it doubles the number parameters for each neuron. Or here's our last one, the soft max activation function. This is it will calculate the probabilities of each class over all possible classes when used for multi-classification models. It returns the probabilities of each class, and the target class will have the high probability of the calculate properties. Probabilities will be in the range of 0 and 1. The sum of all probabilities is equal to 1. Softmax functions is generally used in multiple classifications on the output layer. So again, I said if you look at the transformer architecture, which probably is in this course, you will see it there, and you'll see the other ML models are diagrams for sure. You can only assign a single label to a probability. For this, okay. Let's define an algorithm and a function. So an algorithm is a set of mathematical or computer instructions to perform a specific task. And an algorithm can be composed of several smaller algorithms. You're basically saying, how do you do something? That's what an algorithm is. Right, how are we going to do something? So I want to take a look here at the k-nearest tabber KNN algorithm, which can be used to create a supervised classification machine learning algorithm. So tell me, who are your closest neighbors? And we will infer that I can be considered of the same class. So within can, and you can use different distance metrics, such as Euclidean Hamming, Minkowski Manhattan. So there's all different ones that you can utilize. A function is a way of grouping algorithms together. So you can call them to compute results of. Sounds like a machine learning model, right? Where you have a grouping of algorithms. So look at this k and n just here for a moment. Because we do see this happen a lot, but k nearest neighbor is just like, how close am I from here to here to here to here? It's literally the name. Who are my nearest neighbors? Okay, so KNN itself is not machine learning. But when applied to solve machine learning problem, it makes it a machine learning algorithm, okay? Let's take a look at what a machinery model is. Before we do that, let's define what a model is in general terms. So in general terms, an model is information representation of an object. Person or system models can be concrete. So they have a physical form. Take a design of a vehicle. A person posing for a picture. Then you have abstract, so express as behavioral patterns. Take mathematical computer code. Written word. So what is a machine learning model? Then a demo model is a function that takes in data, performs a machinery algorithm to produce a prediction. The machinery model is trained. Not to be confused with the training model, which is learning to make correct predictions. An ML model can be the training model that is just deployed once it has been tuned to make good predictions. So normally you'd have training data. Let's say label data. And here you are going to have your learning algorithm. And you're going to put it through training. So that's your training model. And then you have hyper-tuning, where you are continuously tweaking the model to get it to where you want it to be, okay? Then once you deploy the model, that is your trained model. Your machine learning model, which can go and produce predictions. And from here, you could then provide it unlabeled data, because its goal is to make predictions. And that could be labeling data or doing other things. Okay, and we call the interaction with the deployed machinery model inference, right? So when you are inferring something, you're providing data and saying, hey, can you make a prediction for me? And that's what inference is, okay? So let's take a look at what a feature is. So a feature is a characteristic extracted from our unstructured data set that has been prepared to be ingested by our machinery model to infer prediction. So ML models generally only accept numerical data. And so we prepare our data into machine-readable format by encoding, which we'll revisit later in more detail. So let's talk about what is feature engineering. So feature engineering is the process of extracting features from our provided data sources. So imagine you have your data sources, which you have then your raw data. You're going to clean and transform them into features, turning them into machine-readable format. Information for your machinery models. And then you go from there, okay? So what is inference? Inference is the active requesting getting a prediction. And when we're talking about in the context of machine learning, we're inputting data into a machine learning model that has been deployed for production use to then open a prediction. So imagine our raw data is a banana and we say, tell me what this is to the machine learning model. It's going to bring back information. So saying it's a yellow banana and has a confidence score of 0.9. So if we talk about the inference textbook definition, it's steps in reasoning, or moving from premise to logical consequence. But I think that it's easy to remember it as the act of requesting and getting a prediction, okay? Let's talk about parameters and hyperparameters. So a model parameter is a variable that configures the internal state of a model and whose value can be estimated. The value parameter is not manually set and will be learned outputted after training. Parameters are used to make predictions that we have model hyperparameter. This is a variable that is external to the model and whose value cannot be estimated. The value of the hyperparameter is manually set before the training of the model. Hyperparameters are used to estimate model parameters. And so we have things like learning rate, epochs and batch size, and here's kind of a diagram. Hopefully it helps make sense. But imagine you have variable. You want to input it into your model, right? And we'll just make a box here to indicate that this is the model, it's gonna go into layers, right? And we'll talk about this again later on. But our parameters are the connections between our nodes. Okay, so the idea is that this will have a variable or a value, it'll have a weight, and those are the